It's a great pleasure for me to participate on this terrific symposium. I'm sorry for not being present, but this is what was possible. So I will share my screen in order to start my talk. All right. So today I will talk about the tipping elements, tipping points in the climate system, and the impact they may have over water availability in tropical South America. At the University of São Paulo, I am coordinating the paleoceanography and paleoclimatology laboratory. I would like you to take away four messages from today's talk. First is that the strength of the Atlantic meridional overturning circulation, or AMOC for short, partially controls long-term tropical South American precipitation. So this will be very important. Second, that AMOC is a tipping element of the climate system that may collapse within the 21st century, and this has drastic impacts over tropical South American precipitation. Paleoclimate archives like marine sediment cores and speleothems allow the investigation of the causes and consequences of an AMOC collapse, and fourth, that a concerted international and multidisciplinary effort is necessary to address the detailed effects of an AMOC collapse over tropical precipitation and ecosystems, building obviously on the fantastic work started by Thomas van der Hamen. When we talk about water availability, we have to consider at least three main elements. First is precipitation, second is evaporation, transpiration, runoff, and infiltration. And third is the various societal demands and pollution. In this talk, I will focus on precipitation and more specifically on tropical South American precipitation. So here we have two maps showing in the top July to August long-term bi-monthly average of precipitation, namely for July and August, and in the bottom, the same for March and April. What we can see in this dark blue band here, latitudinal band, is the tropical rain belt or the intertropical convergence zone that was the topic of many talks today and yesterday. What we can see, and will be important for my specific talk, is that this feature migrates latitudinally, reaching its southernmost position roughly around March to April, as we can see in the bottom map. And this migration is basically, in the long term, controlled by sea surface temperatures in the Atlantic Ocean, if we are talking about the Atlantic ITCZ. And this sea surface temperature gradient in the Atlantic, in turn, is strongly influenced by the Atlantic meridional overturning circulation that is depicted very schematically in this figure here. Here we have a latitudinal cross-section in the Atlantic going all the way from 60 degrees north to 60 degrees south, from the surface to 5,000 meters water depth. And in this red arrow here, we have the AMOC depicted very schematically, in which we have intermediate, central, and surface waters being transported to the north. At the very high latitudes of the North Atlantic, they lose heat to the atmosphere, gain density, sinks to the bottom of the ocean, and flow back to the South Atlantic at deeper water depths. And they upwell around Antarctica, closing this loop. This circulation transports roughly 16 sverdrups of surface waters, also the same amount in the deep ocean. But what is very particular of the AMOC is that it transports heat from the South Atlantic to the North Atlantic in the surface ocean, also at central and intermediate water depth, And this amounts to zero point 0.4 petawatts of energy. This is a huge amount of energy, equivalent to roughly 28,000, the amount of energy produced by 28,000 times the energy produced by the Itaipu hydroelectric power plant, the largest in the southern hemisphere. And this large amount of energy strongly controls in the long term sea surface temperature gradient in the Atlantic. So we can imagine that changes in the strength of this circulation will strongly impact precipitation over tropical South America. This was developed by Pearson and co-authors, and this schematic figure shows a slab ocean, the Atlantic more specifically, and the gray arrows here show the AMOC in very simplified way, in which we have this northward cross-equatorial energy transport. This brings the thermal equator of the Atlantic to be located in the annual average to the north of the geographic equator. Please note here is 0 degrees latitude, and here's 5 degrees north, where we have the location, the annual average location of the tropical rain belt or the intertropical convergence zone. Here we have the two headley cells that try to um, counteract this very strong cross-equatorial heat transport by the AMOC, changing the southward cross-equatorial energy transport by the southern hemisphere headley cell. If we change, very important here is if we change the thermal equator, this whole atmospheric circulation system will shift accordingly, and this may strongly impact tropical South American precipitation, as we will see. But before I go into paleoclimate results, I would like to show this plot, this composite plot of past simulated, past observed, and future modeled strength of the Atlantic meridional overturning circulation. So time is starting here at 1850 and ending 2100 in the right, and black is the past simulated strength of the AMOC anomaly, so that's why we have 0 Sverdrups here. In green, we have this very short, very narrow period of monitored, of observed changes in strength of the AMOC, and all these lines here at your right-hand side, the red, the yellow, and the blue, they all show the future of the AMOC in terms of different emission scenarios of IPCC AR6. All scenarios suggest a decrease in strength in AMOC. This is very important. There is high confidence in this decline, but there is low confidence in the magnitude of the trend. You can see here the error bars. And what is important is that most IPCC models, AR6, they show a salinity bias, and this salinity bias influences very much the AMOC simulation. More importantly, last year, for the very first time, there was a paper in Nature Communications, this one from Deeplefsen and Deeplefsen, that suggested that AMOC may collapse within this very century. And AMOC is a tipping element of the climate system. This is already known. And again, it may collapse within the 21st century, strongly affecting sea surface temperatures and tropical precipitation. But where to look for these possible impacts of changes in AMOC strength over tropical precipitation? No AMOC collapse is recorded in the instrumental record, so we cannot look into the instrumental record. Numerical climate models, at least those used for AR6, have a hard job to simulate tipping elements of the climate system, in the case of the AMOC because of the salinity bias. But the AMOC collapsed in the geological past, and paleoclimate archives like marine sediment cores and speleothems, ice cores, and other, they allow the investigation of the causes and consequences of such events. And now I'm going to the data. So here we compiled 17 sea surface temperature records from the western South Atlantic. You can see the yellow dots here. They show the position of each one of these 17 marine sediment cores, for which we reconstructed sea surface temperatures. Sea surface temperatures were reconstructed for the last 25,000 years. So we are going from the right to the left. So here we have 25,000 years before the present, and here we have the present. Well, during the deglaciation from 19 to 11.7 thousand years before the present, we have this blue vertical bar here that highlights an, a, a very important period of the deglaciation called Heinrich Stadia 1. This is a period where the AMOC was extremely weak or even collapsed. What we can see is a very strong increase in sea surface temperatures in the western South Atlantic. So indeed, data shows that when the AMOC decreases its strength, the South Atlantic increases sea surface temperatures very quickly, and the magnitude of the change is very strong. But now let's see the impact of such a change in sea surface temperatures over tropical South American precipitation. And here I'm showing four downcore records, three from marine sediment cores, and one speleothem record. I will guide you through this plot. There's a lot of information here. Time first is going again from right to left, but here we are not showing the deglaciation and the Holocene. We are showing an interval within the last glacial from 40,000 years before the present to 29,000 years before the present. And the pink vertical bars show two other Heinrich stadios. It means two other periods in which the AMOC was extremely weak. We also have shorter intervals depicted in light blue of uh, also weak AMOC, but these were not as long and as strong as Heinrich stadios, in this case 4 and 3. So if we go from north to south, we're starting with the classic Cariaco Basin record of northernmost Venezuela. We have this reflectance data here in green that shows increase in reflectance values. We have the y-axis flipped here. And this points to decreased precipitation over northernmost South America during weak AMOC periods. The other three records from off the Amazon mouth, the blue one, from off northern northeastern Brazil, the black one, and from Peruvian cave, the gray one, they all show increases in precipitation over tropical South America during these very same events. So far, so good. But we want to look into much more detail about the reaction of tropical precipitation to changes in sea surface temperature in the Atlantic. And therefore, we are focusing on this sediment core here collected off northern northeastern Brazil, roughly 5 degrees south of Brazilian margin. And what we analyzed in here, similarly to other presentations here, was the hydrogen isotopes in plant waxes. This proxy gives us, in this setting, the amount of precipitation. So the lower the values, the more negative the values, the higher the precipitation, and vice versa. And in the horizontal axis, we have here the sea surface temperature in the Atlantic Ocean. And as we go from right to left, we have a warming South Atlantic and a cooling North Atlantic. The color of the symbols here, they show the age of the sample. So it's a little bit a different record, is downcore record, but not plotted against age, right? The age is on the colors of the symbols. And we are going from the LGM in this light blue here and going to the deep ages one, the period when AMOC was extremely weak or even collapsed. So we can see this beautiful linear correlation between these two parameters here, deuterium isotopes in plant wax as a proxy for precipitation over northern northeastern Brazil, and sea surface temperature gradient in the Atlantic. So what we concluded based on this data is that precipitation over northern northeastern Brazil varied synchronously and proportionally with the Atlantic interhemispheric sea surface temperature gradient. And this sea surface temperature gradient in the long term, again, is strongly controlled by AMOC strength, and this relationship is the known thermobipolar seesaw. And this is my last figure in which I would like to show the relationship between different tipping elements of the climate system. Every circle here is a tipping element of the climate system, and the arrows show the relationship between both. Red arrows show destabilizing effect, blue arrows show stabilizing effect, and gray arrows show unclear effect of one tipping element on another tipping element of the climate system. And I'm very much interested on learning what would be the impact of a slowdown of the AMOC in the Amazon rainforest. So, um, apart from deforestation, apart from land use change, apart from fires in the Amazon that are bringing the Amazon close to a tipping point that was very clearly shown by Herman Poveda, we also have to consider a possible impact of changing in AMOC strength on the Amazon rainforest. So far, this signal is unclear, but the talk coming after mine from Thomas Akabani will shed very important light on this topic, and this is extremely new results we have. So, coming back to my takeaway messages, first, the strength of the Atlantic meridional overturning circulation partially controls long-term tropical South American precipitation. Second, AMOC is a tipping element of the climate system that may collapse within the 21st century. Third, paleoclimate archives like marine sediments, paleothemes, and other allow the investigation of the causes and consequences of an AMOC collapse that are very useful in a changing climate, and a concerted international and multidisciplinary effort is necessary to address the effects of an AMOC collapse over tropical precipitation and ecosystems. Many thanks indeed for your attention.